This paper is about the tractability of explaining decisions of classifiers. This is joint work with Joao Marques-Silva at the Amity Institute in Toulouse. So, given a decision taken by a classifier, we can ask the question, what constitutes an explanation of this decision? And what we're interested in is for which classifiers can explanations be produced in polynomial time? And then, what if there are constraints on the possible data? Does this change the complexity? Another question is, are tractable classes identical for explaining positive and negative decisions of a classifier? So, what is a classifier? A classifier is simply a Boolean function tau which takes a feature vector x and returns 0, 1. Typically, x will have perhaps 100 features. For example, if it concerns a person, it might be salary, age, etc. And the question could be, should a bank approve a loan to a customer? This is an example we'll use as our running example. Other examples are, for example, should a student be admitted to a course, or is this tumor malignant? Of course, there are many different applications of classifiers. So we assume we know a classifier, at least we know it in the form of a black box, we can call it. And we have a feature vector, a particular feature vector A, which belongs to a class C, tau A is equal to C, and we need an explanation of it, an explanation for the user, so he/she can understand better the reason for this classification. So there are two possible explanations. One is an abductive explanation, which is a minimal subset of the features which accounts for this decision. In other words, if you fix these features and assign any values to the other features, then you still get the same class. On the other hand, if you're interested in changing the decision, then what you want is a contrastive explanation. This is a minimal set of features which, if changed in A, can lead to a change of class. So let's look at a particular example. This is obviously a toy example where there's only 4 features, and we're supposing that a bank uses this function tau to decide whether to grant a loan to a couple, represented by the 4 features representing their 2 salaries and their 2 ages. Now, suppose that the function is very simple. A loan is granted, in other words, tau is equal to 1, even only if salary 1 is greater than or equal to 30k and age 1 is less than or equal to 60, or the same thing for the second person. So let's see first a couple A, who both earn more than the threshold 30k, and their respective ages are 55 and 65. Then they will be granted a loan, tau A is equal to 1, and an abductive explanation for this is salary 1, age 1. In other words, those 2 features are sufficient for the loan to be granted, whatever the other features. Now let's consider another couple who both earn less than 30k, but are both relatively young. Then there is, in this case, the decision is no, it's tau B is 0, and there is one abductive explanation of this. It's that the 2 salaries are not enough. So the 2 features, sal 1, sal 2. On the other hand, there are 2 contrastive explanations. In order to be granted a loan, they should have a better salary 1 or a better salary 2. So there are values for salary 1 or salary 2 which would allow them to have a loan. So we can see the 2 obvious applications, the 2 different aspects of explanations, abductive or contrastive, which obviously have different uses. So we're going to be looking at threshold classifiers. So this is not really a restriction, but it allows us to use certain results from valued CSPs, for example, to obtain results on explanation. So we suppose that tau is equal to 1 if and only if some real valued function f applied to a feature vector is greater than a threshold t. So This is not, as I said, a really restriction, because we just could replace f by tau. It would still work with t equal to 0. But this is common. It's common to have score-based classifiers. For example, immigration rules in certain countries are based on a score, how much you earn, nationality of your parents, or whatever. So we're looking at classes of functions, families of functions f, which maybe guarantee tractability of explanation. So there are well-known classes of functions. For example, monotone functions. They are defined in the obvious way. If you increase any component, you increase, or at least don't decrease, the value of f. Antitone is simply the opposite, that f is decreasing as the values of x increase. A function is submodular. Submodularity is used in operations research, machine learning, various domains, but this is a formal definition. If you take two vectors x and y, then you take the minimum component y's and the maximum component y's, that gives you two more vectors. If you look at the values of f for these two new vectors, the sum of these values should be less than or equal to the sum of the original values of f applied to x and y. So this class is an abstract definition. This includes all linear functions, for example. It also includes all quadratic functions with negative coefficients of degree 2 terms. So it's you can just, on a simple level, you consider it as an extension of linear functions. Now we'll be needing a particular computational decision problem called tautology. Given a family T of Boolean functions, tautology is the question: can we decide whether a given function tau in this class is a tautology? Is it always equal to 1? This problem is in CoNP, and in fact it's CoNP complete for example, the class of DNFs. Now, finding one abductive explanation, there's a fairly simple algorithm. We start with a hot set of all features. So P is all the features, and then we try and eliminate features. In other words, we free variables. So to start with, P is empty, so trivially we know that we already had a decision of 1, for example. But if we now free features one by one, if the function tau is still tautologous, is still equal to 1 for all the possible values of these free variables, then we can eliminate that feature I from the set of features, and what's remaining at the end is a abductive explanation. What is nice is that we do not need to re-examine features, so it's a linear number of calls to tautology. So, but what in the case of threshold classifiers, what does tautology mean? Tautology means tau is always equal to 1, and in that case, the minimum value of f, score function, must be always greater than t. I mean, the minimum value of f must be greater than t. If we're looking at negative decisions, then we're interested in the question, is tau always equal to 0? Is it unsatisfiable, if you like? And in this case, that's equivalent to saying, is the maximum value of f less than or equal to t, the threshold? So we can see that deciding tautology is equivalent to optimization. So finding an abductive or contrastive explanation of a positive decision is polynomial time if and only if functions in the corresponding class f can be minimized in polynomial time. And for negative decisions, we have to maximize in polynomial time. So examples of classes of functions that can minimize in polynomial time are monotone functions or submodular functions. Maximization is polynomial time, again, for monotone functions, or supermodular functions, which is the opposite of submodular. So now we're interested in extending this result to constrained classifiers. So what do we mean by constrained classifier? So a very, very simple example is consider a medicine that doctors are allowed to prescribe to everybody who has a flu except to pregnant women. Now, an abductive explanation why Alice, who is pregnant, was not prescribed the medicine is that she is pregnant. There is no need to mention that she is a woman, because everyone who is pregnant is a woman. We have this constraint that there are no pregnant men. So this is a constraint on the possible, on the space of feature vectors. It's a physical constraint, real-world constraint. So constraints can be useful to better describe the space of possible feature vectors. And for example, in the use of contrastive explanations, we may use these constraints to, for example, consider age as a constant, whereas salary is not. You can change your salary by getting a better job. You can't reduce your age. It turns out that an abductive explanation of a classifier tau in the context of constraint C is an abductive explanation of the unconstrained classifier tau or not C. Similar for contrastive explanations. So we can see that constrained or non-constrained case, in a constrained or non-constrained case, the tractable classes of finding abductive or contrastive explanations coincide. But as we've seen, the classes differ for positive and negative decisions. So these are some examples, I think the most important ones, of tractable classes of finding explanations. So the first line in this table tells us that if you want to explain a positive decision and your objective function is submodular and the constraints are both max and min closed, then it's possible to find one explanation in polynomial time. If we skip to the fourth line of the table, if the decision is negative, now you need the objective function to be supermodular rather than submodular. And we can see that on the second and fifth lines that monotone functions can be maximized and minimized in polynomial time, but the constraints now must be min closed in positive case, max closed in negative case. So, sorry, I didn't explain what max closed and min closed are, but it's simply if you have two tuples x and y which satisfy a constraint, then you take the maximum at x and y of x and y component-wise, and this also has to satisfy the constraint. That's what max closed means, min closed similarly. So examples of constraints which are both max and min closed, because that seems to be the what's the most interesting case, are, for example, xi is greater than or equal to xj, or a logical constraint which would cover, for example, the case of pregnant, there are no pregnant men, provided you have the right orders in the domains. So we see there exist tractable classes. So, of course, if you give me a black box classifier based on some arbitrary function f, it will not fall in these classes. But if you design your classifier from the outset to be linear, to be monotone or submodular, then you have some interesting tractability results. So it does imply that planning ahead that you need to restrict the possible functions you can use, your possible score functions, to be, for example, submodular or monotone. When accepting, for example, a student on a course, generally the function will be monotone. The higher the marks, the better the student, so more likely we're going to accept him or her. So from a more theoretical point of view, we can ask the question, have we identified all tractable classes? So if we consider the set of threshold classifiers, which are simply the sum of functions fi from some language L, where the scope of each fi is an arbitrary list of features, and the language L is assumed finite, etc. Then we fall exactly on the case of cost function networks. We've basically reduced our problem to minimizing or maximizing a global function composed of cost functions. So it turns out we have a dichotomy for this problem of finding an explanation of decisions of a classifier, which follows directly from dichotomy which is known for languages of cost functions. But as I said, the most important classes are probably monotone, submodular, etc. So to conclude, there are two distinct types of explanation. Abductive and contrastive explanations answer the why and why not questions. Explaining a decision is in general NP hard, but there are interesting tractable classes. For example, based on submodularity or monotonicity, knowing that linearity is a special case of submodularity. So these classes coincide for abductive and contrastive explanations, but not for positive and negative decisions. There is an interesting difference, asymmetry between explaining positive and negative decisions. So in future work, we can look at related problems, because here we've just been looking at finding one explanation. So an obvious question is, can we enumerate all explanations? Well, in almost all cases, the number of explanations can be exponential. So we will be interested in enumerating explanations with polynomial delay, so we can enumerate a certain number of explanations in a reasonable amount of time. Another question we can ask is, for which classes can we find a minimum cardinality explanation rather than minimal for a subset? And for which classes can we find a set of k, for a small value of k, diverse explanations to give a relatively small set of answers to the user? So, for example, for the class of linear classifiers, we know that 1 and 2 are polynomial time, but 3 is NP hard. For the class of monotone classifiers, we have proofs that 1 and 3 are NP hard, and I suspect that 2 is as well. So, but really, apart from linear classifiers, there are very few, there's little hope of finding polynomial time algorithms for anything beyond finding one explanation. Okay, so I'll be very happy to answer questions. Thank you for your attention.